Tonight, we're going to talk about something that sounds like it belongs in a science fiction story, but is happening to you right now, in this exact moment, without you feeling a thing. Time is not passing at the same rate everywhere in the universe. It never has been. And the further you move from where you are standing, the deeper into space you go, the faster you travel, and the closer you move towards something massive, the more violently time bends. But here's what's going to change everything you think you understand about that. In the right conditions, time dilation doesn't just slow your clock by a fraction of a second. It can trap you. It can steal years, decades, centuries from the world you came from while you feel completely normal. And by the end of tonight, you're going to understand exactly how that works, why it happens, and what it would actually mean for a human being caught inside it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the assumption you've been carrying your whole life. The assumption that time just runs. That somewhere in the universe, there's a cosmic clock ticking at the same rate for everyone. A second here on Earth is the same second passing on the International Space Station. The same second ticking away on a spacecraft heading toward Mars. The same second that passed for every human who ever lived. That assumption feels so obvious, it barely registers as an assumption. It feels like bedrock. It's the kind of thing you'd never question, the way you'd never question whether the floor beneath you is real. You stand on it. You trust it. It's just there. And yet, in 1905, a 26-year-old Swiss patent clerk named Albert Einstein published a paper that revealed this bedrock assumption was wrong. Not wrong in some minor technical way that physicists argue about in journals. Wrong at the foundation. Wrong in a way that changes what time actually is. Einstein's special theory of relativity started with two postulates. Two things, he insisted, had to be true, even if the consequences were impossible to accept. The first was that the laws of physics are identical for every observer in uniform motion. It doesn't matter if you're sitting still or moving at a constant speed in a straight line. The equations describing how the universe works are the same for everyone. You can't detect absolute motion through any experiment. There is no preferred standstill. The universe has no fixed background against which all motion is measured. The second postulate was the one that caused all the trouble. The speed of light is constant for all observers. Not just roughly constant. Not constant unless you're moving toward the light source. Not constant unless you're in a special state of rest. Exactly constant. Always the same, in every direction, at every speed. For every observer, anywhere in the universe. 186,000 miles per second. No exceptions. That sounds simple. It's not. To see why, consider what physicists call Galilean relativity. Galileo established something now so obvious, it seems trivial. If you're on a ship moving at 20 miles per hour and you throw a ball forward at 30 miles per hour, a person watching from the dock sees that ball moving at 50 miles per hour. You add the speeds. The speed of an object equals your speed plus the object's speed relative to you. This works perfectly for every object we deal with in everyday life. Rocks, planes, cars, baseballs. All of them obey this intuitive rule. Now, apply it to light. Imagine a spacecraft moving at 90% of the speed of light. Someone on that spacecraft shines a flashlight forward. By Galilean addition, That light beam should be moving at 190% of the speed of light relative to you watching from the ground. 186,000 miles per second from the ship, plus another 167,000 miles per second from the ship's velocity, adding up to something faster than light. But experiments showed it doesn't work that way. The light beam doesn't arrive any faster. It arrives at exactly 186,000 miles per second, the same speed it always has, regardless of how fast the ship is moving. This result was so strange that physicists spent years trying to find a mistake in the experiments. The most famous attempt was the Michelson-Morley experiment in 1887. Albert Michelson and Edward Morley built an incredibly sensitive interferometer, a device that could detect differences in light speed of 1 part in millions. They reasoned that if there was some kind of fixed medium through which light traveled, something they called the luminiferous ether, then Earth's motion through that ether should produce a measurable difference in the speed of light measured in different directions, like the difference between swimming with a current versus against it. They found no difference. None. The speed of light was the same in every direction, no matter how Earth was oriented, no matter what time of year they measured. The ether didn't exist. And if the ether didn't exist, if there was no fixed background against which motion could be measured, and if the speed of light was the same for everyone regardless of their motion, then something very strange had to be true about space and time themselves. Einstein was the first person to follow the logic all the way to its conclusion without flinching. If the speed of light is fixed, and speed is distance divided by time, and the speed stays the same for everyone, then distance and time cannot both be fixed for all observers. Something has to give, and what gives is time. When you move faster, time runs slower for you than for the people you left behind. Not as a feeling, not as a perception. Literally, mechanically, measurably slower. This is called time dilation, and it is the most counterintuitive truth in all of physics. Here's the simplest way to see why the mathematics demands it. Picture 2 people, one standing still, one moving. Both are holding clocks. Both clocks work by bouncing a light pulse back and forth between 2 mirrors separated by a fixed distance. Each bounce counts as 1 tick. Now the moving person's clock travels forward horizontally as the light bounces vertically between the mirrors. From the stationary person's perspective, the light in the moving clock has to travel a longer diagonal path with each bounce. The light doesn't just go straight up and straight down. It has to travel up and forward, then down and forward, tracing a zigzag path through space. But light always moves at the same speed. If the path is longer and the speed is constant, each bounce takes more time. The moving clock ticks more slowly. The stationary person watches the moving clock and sees it running behind. This isn't a measurement error. It isn't a mechanical problem with the clock. It's what time is actually doing. The moving person experiences fewer seconds per hour than the stationary person. They age more slowly. They live in a compressed version of time without noticing it at all. Because from inside the moving reference frame, everything feels exactly normal. Their heartbeat feels normal. Their thoughts feel normal. Their clock says the right time. From their point of view, they're standing still. It's the external universe that's moving. And from their point of view, they watch the stationary person's clock ticking slowly. Both observers see the other person's clock running slow. Both are correct within their own reference frames. The weirdness only becomes physical and undeniable when the two observers come back together, when the moving person slows down, reverses direction, and returns. At that moment, the symmetry breaks. And when they stand next to each other again, less time has passed for the one who moved. The universe would have moved forward more for one person than the other. They would have taken different routes through time. And the difference is not a matter of perception or interpretation. It's written in biology, in the number of heartbeats that occurred, in the number of times their cells divided, in the physical age of their bodies. Now here is the question that separates theory from reality. Does any of this actually happen? Yes. On October 4th, 1971, two physicists named Joseph Hufferley and Richard Keating boarded commercial airplanes. Not a rocket, not a space shuttle, a regular commercial jet carrying ordinary passengers and ordinary cargo, making ordinary flights. They brought 4 cesium atomic clocks. These weren't ordinary clocks. Cesium atomic clocks keep time by counting oscillations of cesium, 133 atoms. Those oscillations are extraordinarily regular. So regular that the cesium atom's natural frequency is now the official definition of the second. 1 second equals 9,192,631,770 oscillations of the cesium 133 atom. These are the most precise timekeepers humans had ever built at that point. Hufferley and Keating flew east around the world with these clocks. Then they flew west around the world. Then they brought those clocks back to the United States Naval Observatory and compared them with identical clocks that had stayed on the ground the whole time. The clocks that flew didn't agree with the clocks that stayed. The differences were tiny, measured in nanoseconds, billionths of a second, but they were exactly what Einstein's equations predicted. Not approximately, not in the right ballpark. Exactly. The eastbound clocks, which were moving faster relative to Earth's center than the ground clocks because they were traveling with Earth's rotation, ran slower due to velocity. The westbound clocks, moving against Earth's rotation and thus slower relative to Earth's center, ran faster due to lower velocity. Both sets of clocks also ran faster than the ground clocks due to gravitational time dilation being at higher altitude in a weaker gravitational field. Both effects showed up. Both matched the math. Hufferley and Keating didn't discover time dilation. They confirmed it so precisely that it could never seriously be questioned again. This was not a fringe experiment. It was published in the journal Science. It was replicated. It's been replicated many times since, with much more precise equipment. The result is always the same. Time is not fixed. Time depends on motion and gravity. And the faster you move, or the stronger the gravity around you, the more dramatically time diverges from the rate experienced by someone else. You probably used time dilation today and didn't think about it once. The global positioning system depends on a network of 31 active satellites orbiting Earth at about 12,500 miles altitude. Those satellites carry atomic clocks. Your phone talks to those clocks to figure out where you are. But here's the problem. Those satellites are moving fast. About 8,700 miles per hour. At that speed, the clocks on board run slow compared to clocks on Earth's surface. They lose about 7 microseconds per day due to velocity. 7 millionths of a second. That sounds trivial, except that GPS navigation works by calculating how long a signal takes to travel from a satellite to your phone. The signal travels at the speed of light. At the speed of light, 7 microseconds corresponds to about 1.3 miles of error. Every day. Accumulated. In roughly 2 minutes of operation, a GPS system ignoring this effect would be off by enough to put you in the wrong neighborhood. But velocity isn't the only factor. The satellites are also at high altitude, where Earth's gravity is weaker. Weaker gravity means time runs faster for them. This effect is even larger. The satellites gain about 45 microseconds per day from reduced gravity. Combined, the net difference is about 38 microseconds per day, faster than Earth clocks. GPS engineers correct for this with precision. They program the satellite clocks to run slightly slower before launch, so that once they're in orbit and the relativistic effects kick in, the clocks end up synchronized with the ground. If they didn't do this, GPS would accumulate about 7 miles of error per day. No satellite navigation would work. No drone deliveries. No precision agriculture. No autonomous vehicles. No emergency services locating a caller. Every GPS device on Earth depends on engineers having accounted for the fact that time runs differently at different speeds and altitudes. Time dilation is not abstract. It is infrastructure. The most precise positioning technology in the history of human civilization is built on top of the physics that says time is not the same everywhere. Einstein never built a GPS receiver, but every GPS receiver is a monument to the correctness of what he worked out. Now, let's talk about what this means for a human body. In 2015, astronaut Scott Kelly left Earth and boarded the International Space Station. He stayed for 340 consecutive days. This was part of NASA's Year in Space mission, designed specifically to study the long-term effects of spaceflight on human biology. While he was gone, his identical twin brother, Mark Kelly, stayed on Earth. Mark was also a former astronaut, also in excellent physical condition. They were genetically identical. They grew up together, trained together, served in the Navy together. Before Scott launched, the twins were measured, sampled, tested on every dimension their doctors could think of. The idea was to have as close to a perfect control experiment as biology permits. One twin in space. One twin on the ground. See what space does to a human being that Earth doesn't. And then, for nearly a year, one of them moved through time at a slightly different rate. The ISS orbits at about 17,500 miles per hour. That's fast enough for velocity time dilation to matter. But the ISS is only about 250 miles up, where gravity is still about 90% as strong as it is on the surface. The two effects, velocity slowing the clock, reduced gravity speeding it up, mostly cancel out, with velocity winning slightly. When Scott Kelly came home, he had aged about 5 milliseconds less than his brother. 0.005 of a second. Across an entire year. It's almost nothing. Barely measurable. But it wasn't nothing. Scott Kelly came back younger than his twin. By 5 milliseconds, he was the younger brother. Not by perception, not by feeling, by physics. The universe had processed fewer seconds for him. And the biological effects went further than just clocks. NASA's twin study revealed changes in Scott's gene expression. The way his genes were being read and translated into proteins shifted during spaceflight. His gut microbiome changed composition. His cognitive function showed subtle shifts. His telomere length, the protective caps on the ends of chromosomes, associated with biological aging, actually lengthened during flight, then returned toward baseline after landing. Some changes reversed after he returned to Earth. Some didn't fully reverse. The human body isn't just a mind riding around in a machine. It's a biological system tuned for one specific gravitational environment, one specific radiation environment, one specific daily cycle of light and darkness. Move it somewhere else, at a different speed, and the tuning shifts. Time dilation is only one piece of what spaceflight does to a human body. But it's the piece that has no antidote. You can't unage. You can't get those 5 milliseconds back. They're gone. Or rather, they were never spent. They simply didn't happen. 5 milliseconds is not what this video is about. 5 milliseconds is just where it starts. Because the math of time dilation doesn't grow linearly with speed. It grows according to what's called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who worked out the mathematical structure of these transformations in the years just before Einstein published Special Relativity. Lorentz had the math. Einstein understood what the math meant. The Lorentz factor is calculated from a simple formula. You take the object's speed as a fraction of the speed of light. You square it. You subtract it from 1. You take the square root of what's left, and you divide 1 by that result. The Lorentz factor starts at 1 when you're not moving and climbs toward infinity as you approach the speed of light. The time dilation factor is equal to the Lorentz factor. A Lorentz factor of 2 means time runs twice as slowly for the moving observer. A factor of 10 means time runs 10 times more slowly. A factor of 100 means 100 times more slowly. At 10% of the speed of light, the Lorentz factor is about 1.005. Time runs about 0.5% slower for you than for someone standing still. Not dramatic. Noticeable to a precise instrument, invisible to a human. At 50% of the speed of light, the Lorentz factor is about 1.15. You age 15% more slowly. A year of travel takes about 13.5 months of time back home. Still manageable. At 90% of the speed of light, the Lorentz factor is about 2.3. You age less than half as fast as someone on Earth. A year of travel corresponds to roughly 2.5 years back home. At 99% of light speed, the Lorentz factor is about 7.1. 1 year of your travel equals 7 years on Earth. At 99.9% of light speed, the Lorentz factor is about 22. 1 year of your experience equals 22 years back home. At 99.99% of light speed, the Lorentz factor is about 71. 1 year of your travel equals over 70 years on Earth. At that last speed, you could leave Earth at 25 years old, spend what feels like a single year cruising near the speed of light, and come back to find that everyone you knew is either very old or gone. Your parents, your siblings, your friends, your colleagues. 70 years passed without you, and you didn't experience 70 years. You experienced one. You look the same. You feel the same. You just live in a world where everyone you loved has moved through a lifetime without you. This is the trap. Not a dramatic catastrophe. Not a technical failure. Just physics, doing exactly what it's supposed to do. The equations describe this perfectly. but human intuition doesn't accept it without a fight. So let's deal with the objection head-on. It's called the twin paradox. And for decades, it was treated as a genuine problem with relativity. It goes like this. If you leave Earth and travel fast, you age more slowly. But motion is relative. From your perspective on the ship, you're standing still. Earth is the thing moving away from you at near light speed. So shouldn't Earth age more slowly from your point of view? Why does your twin on Earth age faster and not the other way around? This seems like a real contradiction. If both observers see the other one's clock running slow, how does one person end up actually physically younger when they meet again? The resolution is simple, but not obvious. The effects are not symmetric. They only seem symmetric if you ignore one thing: acceleration. At some point in the journey, the ship turns around and comes back. To do that, it has to decelerate. Stop. Accelerate again in the opposite direction. That acceleration breaks the symmetry. The ship's occupant experiences a force. A real, physical, measurable force pushing them back in their seat. The person on Earth does not experience that force. There is no ambiguity about who was in motion. The traveler changed reference frames. The person at home didn't. When you account for what happens to simultaneity during the acceleration phases, and this part requires general relativity to work out fully, the math resolves perfectly. The traveling twin is younger, always. The twin paradox is not a paradox at all. It's a misunderstanding of what relativity actually says. The universe is self-consistent. It has to be. And when you work out all the details, including the parts that seem paradoxical, it always is. The experimental evidence that makes this undeniable doesn't come only from satellites and atomic clocks. It comes from particles so small they exist for a tiny fraction of a second: muons. When high-energy cosmic rays, protons streaming from distant supernovae, from active galactic nuclei, from the most violent events in the universe, slam into Earth's upper atmosphere about 10 miles up, they produce a cascade of particles. Among them are muons. A muon is an elementary particle, heavier than an electron but belonging to the same family. It has a mass about 207 times that of an electron, and it's unstable. It decays into an electron and 2 neutrinos. In a laboratory at rest, the average muon lives for about 2.2 microseconds. 2.2 millionths of a second. In 2.2 microseconds, even traveling at the speed of light, a muon can only cover about 2,000 feet, less than half a mile. They're created 10 miles up. They should barely make it a fraction of the way down before disappearing. They should never reach sea level, but they do. Detectors on the ground catch them constantly. Billions of them every day. The answer is time dilation. Muons, produced by cosmic ray collisions, travel at roughly 99% of the speed of light. At that speed, the Lorentz factor stretches their lifespan by about 7 times from our perspective. Instead of 2.2 microseconds, they effectively live for about 15 microseconds as seen from the ground, long enough to travel several miles. Which is why we can detect so many of them at sea level. From the muon's perspective, by contrast, it still only lived 2.2 microseconds. But the distance it had to travel was Lorentz contracted. 10 miles of atmosphere compressed down to less than half a mile from the muon's frame of reference. It survives the journey because from its point of view, the journey was short. From ours, it survived because time passed more slowly for it than for us. Both descriptions are correct. They describe the same event from different frames of reference. And in both cases, the muon reaches the ground. Every muon detector on Earth is running a live experiment confirming that time dilation is real, not approximately real. Measurably, precisely, indisputably real. They didn't sign up for the experiment. Physics drafted them. And physics has been drafting muons into this experiment continuously, for every second that cosmic rays have been hitting Earth. Now, let's go somewhere more extreme. We've been talking about velocity. But Einstein didn't stop there. His general theory of relativity, published in 1915, extended the framework to include gravity. And it revealed something that makes the velocity effects look modest. The central insight of general relativity is that gravity is not a force. This is the part that sounds like philosophy, but is actually physics. Newton described gravity as a force acting between masses, a force that reaches across space instantly, pulling things together. That picture works extremely well for most purposes. It correctly predicts planetary orbits. It correctly predicts how objects fall. It's accurate enough to land spacecraft on other planets. But it's not what gravity actually is. Einstein's picture is different. Mass curves, spacetime, not just space. Spacetime. The four-dimensional fabric that contains everything. A massive object creates a curvature in that fabric, and other objects moving through the fabric follow the curves. What we experience as the force of gravity is actually the effect of moving through curved spacetime. When you drop a ball, it doesn't fall because something is pulling it. It falls because the curved geometry of spacetime near Earth points that way. The ball is following the straightest possible path through curved spacetime, and that path curves downward. Now, here's what this means for time. Curved spacetime doesn't just bend the paths of objects, it bends time. Specifically, the deeper you are in a gravitational well, the more spacetime is curved around you, and the slower time moves for you relative to someone in flatter, weaker gravity, spacetime. This is gravitational time dilation, and it's distinct from velocity-based time dilation, though related. You don't need to be moving. You just need to be near something massive. The clock at the bottom of a mountain runs slightly slower than the clock at the top, not because of any mechanical difference between the clocks. Not because the clock at the bottom is shaken more by vibrations. Because the bottom of the mountain sits deeper in Earth's gravitational field, where spacetime is more curved, where time genuinely runs more slowly. The difference on Earth is tiny. Your feet age infinitesimally slower than your head, always, because they're closer to Earth's center. About 30 nanoseconds per year across your body height. Too small to feel. Too small to ever matter practically. But real. And in 1959, it was confirmed in an experiment of breathtaking elegance. Robert Pound and Glenn Rebka set up their apparatus inside Jefferson Laboratory at Harvard University. They placed a gamma-ray source in the basement, a detector at the top of a tower about 22.5 meters tall, 74 feet, the height of a 6-story building. They measured whether gamma rays lost energy climbing those 74 feet against Earth's gravity. Now understand what they were actually looking for. A gamma ray emitted by an atom has a very specific frequency, like a tuning fork that vibrates at exactly one pitch. If time runs at a different rate at the top of the tower than at the bottom, then the frequency of the gamma ray, as measured at the top, should be slightly different from what was emitted at the bottom. Not because the gamma ray was affected in flight, but because the rate at which oscillations are counted is different at different heights. The clock ticking at the bottom emits a certain number of wave crests per second of bottom clock time. But the clock ticking at the top counts fewer of those crests per second of top clock time, because top clock time runs faster. The light appears red-shifted, stretched toward longer wavelengths, lower frequency. The predicted shift was about 2.5 parts in 1,000 trillion, a fraction so small it barely has a name. Roughly 1 part in 400 trillion. They measured it. They confirmed it. Even across a height of 74 feet, gravity bends time measurably. This is the Rebka experiment. It remains one of the most elegant confirmations of general relativity ever performed. Not at a black hole, not in space, in a building on the Harvard campus. The universe is very thorough about applying its physics. If you want to see what gravitational time dilation looks like at genuine extremes, you need to look at what the universe makes when stars finish burning. A neutron star is what remains. After a massive star, somewhere between about 8 and 20 times the mass of our Sun exhausts its nuclear fuel and can no longer support itself against gravity. The outer layers explode outward in a supernova, one of the brightest events the universe produces. The core collapses inward in less than a second. If the remaining mass is between roughly 1.4 and 2 to 3 times the mass of the Sun, the collapse is halted by quantum mechanical pressure. The protons and electrons in the core are crushed together into neutrons, and the neutrons resist further compression through a quantum mechanical effect called neutron degeneracy pressure. The result is a neutron star, an object about 12 to 15 miles across, packed with more mass than our Sun. The density at the core of a neutron star is comparable to the density of an atomic nucleus. A single teaspoon of neutron star material would weigh about 10 million tons on Earth. 10 million tons in a teaspoon. The surface gravity of a neutron star is roughly 200 billion times Earth's surface gravity. Under that gravity, spacetime is dramatically curved, and the gravitational time dilation is correspondingly dramatic. A clock sitting on the surface of a neutron star would run at about 70 to 80% the rate of a clock far away in flat space. For every second you experience on the surface, about 1.2 to 1.4 seconds pass in the universe beyond. You could stand there, if standing there were even remotely conceivable, which it is not, and age measurably more slowly than the rest of the universe. The problem is everything else about being on a neutron star. The surface gravity would compress any material far beyond its structural limits. The magnetic field of a typical neutron star is trillions of times stronger than Earth's. At such field strengths, atoms themselves are distorted into thin, elongated shapes aligned along the field lines. Chemistry as we know it stops working. Biology as we know it stops working. Anything biological in the vicinity of a neutron star would be disassembled at the atomic level long before it got close enough for the time dilation to matter. But the clock on the surface is still running slow. The universe is keeping the record, whether or not anyone is left alive to read it. Now, let's go somewhere. Gravity makes neutron stars look mild. A black hole, the object at the center of the most dramatic consequences of time dilation in the known universe. When the collapsing core of a massive star contains more than about 2 to 3 times the mass of the Sun, neutron degeneracy pressure isn't enough to stop the collapse. The collapse continues and continues. There is nothing in known physics that can stop it. The matter doesn't find a new equilibrium. It just keeps falling inward. What forms is a region of space-time so curved that not even light can escape from within a certain radius. That radius is the Schwarzschild radius, named after Karl Schwarzschild. He was a German physicist and astronomer, a brilliant man who held positions at the observatory in Göttingen and later at the Berlin Observatory. In 1915, at the age of 42, he was serving in the German army on the Eastern Front during the First World War, having volunteered despite his age. The conditions were brutal. The fighting was grinding and relentless. And yet, somehow, while stationed in those trenches, Schwarzschild found time to read Einstein's newly published General Relativity papers. Within weeks of reading them, he solved Einstein's field equations, exactly something no one else had done, and something Einstein himself hadn't been sure was possible in closed form. He mailed the solution to Einstein. Einstein was astonished. He presented Schwarzschild's result to the Prussian Academy of Sciences in January of 1916. Schwarzschild died in May of 1916 of a disease contracted at the front. His solution outlived him by more than a century. And hidden inside that solution was a boundary. At a specific radius from the center of any sufficiently massive and compact object, something strange happens. At that radius, the curvature of space-time becomes so extreme that the escape velocity, the speed an object would need to reach in order to escape the gravitational pull, equals the speed of light. Inside that radius, nothing can escape. Not matter, not light, not information, nothing. That boundary is called the Schwarzschild radius. The spherical surface it defines is the event horizon, and the object it surrounds is a black hole. For an object with the mass of our Sun, the Schwarzschild radius is about 1.8 miles. Compress all of the Sun's mass, more than 300,000 times the mass of Earth, into a sphere less than 2 miles across, and you have a black hole. For the supermassive black hole at the center of our galaxy, which we call Sagittarius A, with a mass of about 4 million solar masses, the Schwarzschild radius is about 8 million miles, about 9 times the diameter of the Sun. For the black hole at the center of the galaxy, M87, imaged by the Event Horizon Telescope in 2019, the mass is about 6.5 billion solar masses. Its event horizon spans about 24 billion miles, large enough that our entire solar system out past the orbit of Neptune, a span of roughly 5.5 billion miles across, could fit inside it with room to spare. These are real objects, real places in the real universe. And near them, time dilation becomes not just interesting physics, but something with genuine consequences for anything that ventures close. Now, let's talk about what time dilation does near an event horizon. As you approach a black hole, gravity grows stronger. And as gravity grows stronger, time slows down. Imagine watching someone fall toward an event horizon from a safe distance. As they fall, you watch them slow down. Not because they've stopped accelerating, they're accelerating the entire time, falling faster and faster from their own perspective. But from your perspective, their time is running slower and slower. The light they emit is stretched to longer wavelengths as their photons climb out of the deepening gravity well. They appear to redden, fade, and move in slower and slower motion. As they approach the event horizon itself, their apparent motion slows to a near standstill. From your perspective, they never fully cross the horizon. They freeze. A ghost image hanging at the edge of infinity, growing dimmer as the redshift stretches their radiation below any possible detector's sensitivity. They simply fade out of the universe. And from their own perspective, they notice none of this. They feel the acceleration of freefall. They cross the horizon. They might not even know the exact moment they crossed, because for a sufficiently large black hole, the tidal forces at the event horizon are gentle. There's no wall to feel, no flash of light, no sensation of crossing, just the continuation of free fall. But the universe outside has moved on without them, an enormous amount. And once inside the event horizon, they can't send any signal back out, not even a goodbye. Because inside the event horizon, even light cannot climb out. Every path forward leads to the singularity, not a place in space, a moment in time. Inside a black hole, the singularity is not something you can navigate around. It's not a rock in space. It's the future. It is in the future of every possible trajectory inside the event horizon. There's no route that avoids it, because it's not a where, it's a when. Let's make this concrete with a scenario. A spacecraft parks in a stable orbit close to a stellar mass black hole. Close means at the innermost stable circular orbit. For a non-rotating black hole, this sits at 3 times the Schwarzschild radius. At that distance, time runs at approximately 81% of the rate experienced far from the black hole. That means for every year the crew spends in that orbit, about 1.2 years passes in the distant universe. Not dramatic. A few months difference per year. But it accumulates. 10 years in that orbit, 12 years pass far away. Now make the black hole spin. Most black holes rotate. Matter, falling in, carries angular momentum, and black holes conserve angular momentum. A spinning black hole drags space-time itself around with it. This is called frame dragging. Space physically rotates near a spinning black hole. If you tried to hold perfectly still near a spinning black hole, the very fabric of space-time would be sweeping you around. You'd need to fire engines constantly just to maintain your orientation. A spinning black hole also allows the innermost stable circular orbit to sit much closer to the event horizon than is possible around a non-rotating black hole. For a maximally spinning black hole, the innermost stable orbit sits at the event horizon itself. At orbits close to the event horizon of a rapidly spinning black hole, the time dilation is severe. Hours outside the orbit could correspond to weeks inside it. The film Interstellar depicted a version of this, characters experiencing 1 hour near a black hole, while years passed for someone waiting far away. The film's physics consultant was Kip Thorne, who won the Nobel Prize in Physics in 2017 for his role in the first detection of gravitational waves. The specific scenario in the film was tailored for dramatic effect rather than strict physical plausibility, but the phenomenon it depicted is real. Severe time dilation near the event horizon of a rapidly spinning black hole is not science fiction. It is what Einstein's equations predict. And Einstein's equations have been right about everything we've ever tested them against. But there's a subtler layer to all of this, one that most treatments of time dilation skip. And it's important for understanding why time dilation isn't just a curiosity about fast-moving objects or extreme gravity. It changes the very concept of time itself. It concerns something called simultaneity. On Earth, we take it for granted that when two things happen at the same time, that's an objective fact, a neutral fact of reality, the same for everyone. In 1905, Einstein showed that this is not true. Whether two events happened at the same moment depends on who's asking. Specifically, it depends on the observer's state of motion. Two observers moving at different velocities can genuinely, legitimately, correctly disagree about whether two events happened simultaneously. This isn't a measurement error. It isn't a communication delay. It's a fundamental property of how space-time works in a universe where the speed of light is finite and constant for all observers. Here's why it happens. Suppose you're on a very long train, moving at high speed. Lightning strikes both ends of the train simultaneously, according to a person standing at the midpoint of the train. The light from both strikes reaches that midpoint observer at the same time. They conclude the strikes were simultaneous. But a person standing on the platform watching the train go by sees something different. They see the train moving forward. The light from the front strike has to travel backward against the train's motion to reach the midpoint observer. The light from the rear strike has to travel forward with the train's motion to reach the midpoint observer. From the platform observer's perspective, the rear strike happened first. The front strike happened after. The two events were not simultaneous. Who is right? Both of them. There is no absolute fact about whether the two lightning strikes happened simultaneously. There is only what simultaneity means in a given reference frame. And different reference frames have different answers. This means there is no universal now. There's no cosmic moment that is the present for all observers everywhere in the universe. Each observer carries their own version of now with them. And when observers are moving relative to each other at large fractions of the speed of light, their versions of now can be dramatically different. What you calculate to be happening right now on a planet 100 light-years away depends on how fast you're moving toward or away from that planet. Change your velocity, and your now at that planet shifts. Not by seconds or minutes, by years. There is no objective fact about what's happening right now on the other side of the galaxy. The question has no single correct answer. It has many correct answers, depending on who's asking. This is one of the most deeply strange implications of special relativity. And it's not speculation. It's mathematics. Mathematics that has been confirmed by every precision experiment ever designed to test it. Now let's scale this up to something humans might actually try to do. Interstellar travel. The nearest star system, Proxima Centauri, is about 4.24 light-years away. That's about 25 trillion miles. If you left Earth tomorrow on the fastest spacecraft we've ever built, the Parker Solar Probe, at its maximum speed of about 430,000 miles per hour, you would arrive in roughly 6,500 years. Your entire civilization would have risen and fallen before you got there. So to make interstellar travel feasible within a human lifetime, you need to travel at relativistic speeds. And when you do, time dilation becomes one of the most practically significant consequences of your journey. At 10% of the speed of light, a round trip to Proxima Centauri and back would take about 85 years for observers on Earth. For the crew, it would feel like about 84 years and a few months. Barely any difference. At 50% of light speed, the Earth frame round trip takes about 17 years. The crew experiences about 14.5 years. You'd miss about 2.5 years of Earth history you didn't live through. At 90% of light speed, the Earth frame round trip takes about 9.5 years. The crew experiences about 4 years. 9.5 years have passed on Earth. You've aged 4. Your younger sibling is now older than you. At 99% of light speed, the Earth frame round trip takes about 8.5 years. But the crew experiences about 14 months. You aged a little over a year. Earth aged 8.5. At 99.9% of light speed, the Earth frame trip takes about 8 years and a few months. The crew experiences about 140 days. A little under 5 months. You leave in the spring. You're back before the year is out. And on Earth, 8 years have passed. At 99.99%, the crew experiences about 44 days. Earth, over 8 years. 44 days of travel. 8 years of history you skip. No one paused for you. They didn't wait. They couldn't. Time kept running for them. You just weren't in it. The further down this path you go, the stranger the mathematics becomes. The closer you get to light speed, the more your journey compresses in your experience and expands in everyone else's. You could theoretically cross the observable universe, 93 billion light-years, in a single human lifetime, if you could approach close enough to light speed. The universe is 93 billion light-years across, and you could cross it before you turned 70. But when you arrived, trillions of years would have passed back home. Every star that existed when you left would have burned out. Every galaxy would have aged past recognition. The cosmic microwave background would have cooled to near absolute zero. You'd have outlasted the active universe, and you'd have nowhere to return to. That's the trap in its ultimate form. Not a prison with walls. A prison made of the structure of space-time itself. Made of geometry. Made of the fact that the faster you move, the slower you age, and the faster the universe ages around you. And there is no way to outrun the trade. There's a deeper layer to all of this that most treatments of time dilation skip, and it's important. It concerns what time actually is. Not in the philosophical sense, in the physical sense. Einstein's equations describe a four-dimensional structure called spacetime. 3 dimensions of space, 1 of time, woven into a single fabric. Objects don't move through space separately from moving through time. They move through spacetime. They trace paths through this 4-dimensional structure called world lines. A world line is your complete history. Every position at every moment. If you're sitting still in your chair right now, you're not going anywhere in space. But you're absolutely moving through time. Your world line is being drawn right now, moment by moment, forward through the time dimension. Every particle in the universe has a world line. Every object, every event. Now here's the key. Different world lines have different lengths. Not in the spatial sense, in the temporal sense. The technical term is proper time, the time measured by a clock that travels along a specific world line. And in space-time geometry, the math is counterintuitive. In ordinary 3-dimensional space, The straight line is the shortest path between 2 points. In four-dimensional spacetime, the straight world line, the one that doesn't accelerate, turns out to be the one with the most proper time between two events. A curved world line, one that deviates from straight motion, covers less proper time. The twin who stays on Earth follows a nearly straight world line. The twin who travels follows a curved world line, bending away from Earth and back. The curved path covers less proper time. That twin ages less. This is not arbitrary. It's the geometry of space-time itself. Your age, your actual biological age, is the length of your world line measured in proper time. And if you take a curved path through space-time by accelerating, by orbiting, by falling in and out of gravitational fields, you accumulate less proper time than you would on a straighter path. You come back younger. Not because of any trick or illusion, because of the geometry of the universe you live in. Let's look at one more piece of evidence. It comes from exploding stars. In the 1990s, astronomers were trying to figure out whether the universe's expansion was slowing down or speeding up. They used a type of supernova, a type 1a, supernova as what astronomers call a standard candle. A type 1a supernova happens in a binary star system when a white dwarf accumulates enough mass from a companion star to trigger a thermonuclear explosion. Because the explosion always happens at essentially the same mass threshold, about 1.4 times the mass of our Sun, a threshold called the Chandrasekhar limit the peak brightness is always roughly the same. Two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, were measuring distant supernovae in the late 1990s. They expected to find that the expansion of the universe was gradually slowing down. Gravity, they reasoned, should be pulling everything back together. They found the opposite. The universe's expansion is accelerating. Something is pushing space apart faster and faster. Something we now call dark energy, though that name is basically an admission that we don't know what it is. Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize in Physics in 2011 for this discovery. But hidden inside that discovery was something else. The light curves of those distant supernovae, the way their brightness rose and fell over time, were stretched. They faded more slowly than nearby supernovae, not because the explosions were different, because the supernovae were receding from us at high speed, and objects moving away from us experience time dilation. From our perspective, the physical processes of the explosion, the rate at which it brightens, the rate at which it fades, all ran slower. The explosion was in slow motion. Not because anything was wrong with it, because it was moving. Cosmological time dilation. The same effect that slows a muon, that shifts a GPS satellite's clock, that would steal years from an interstellar traveler operating at the scale of the universe itself. Ancient supernovae running at a measurably slower pace because of the speed at which the universe is expanding. Every measurement points in the same direction. Time is not fixed. Time is not the same for everyone. Time is a dimension of the universe, and like the spatial dimensions, it responds to mass and to motion. There is no cosmic clock ticking for everyone. There never was. What does this mean for the future of human beings in space? Not in the science fiction version, where we have warp drives and inertial dampers and ships that can get anywhere in minutes. In the real future, the one constrained by actual physics. The first thing to accept is that the energy requirements for relativistic travel are staggering. The kinetic energy of an object increases with the Lorentz factor. To accelerate a spacecraft to 90% of light speed, you need to supply roughly 1 1/3 times its rest mass energy worth of kinetic energy. For a modest spacecraft of 10,000 kilograms, that's about 1 × 10⁻21 joules. The entire world currently produces about 6 × 10⁻20 joules of energy per year from all sources combined. So just accelerating one small ship to 90% of light speed would take close to 2 years of the entire planet's energy output. For 99% of light speed, the energy requirement climbs further. For 99.9%, it climbs again, more steeply. There's no gentle slope here. Every decimal point closer to light speed costs dramatically more energy. This isn't an engineering problem that will be solved by a breakthrough material or a more efficient engine. It's a consequence of the Lorentz factor itself, which grows without bound as speed approaches light speed. The universe is very clear about this. Infinite energy is required to actually reach light speed. You can get close, arbitrarily close, in principle. But close has a cost, and that cost becomes unmanageable at the percentages where time dilation becomes interesting for practical purposes. We are nowhere near having the energy production, or the storage, or the propulsion systems to make any of this real. The fastest thing we've ever built, the Parker Solar Probe, reaches roughly 0.064% of the speed of light. The time dilation at that speed is 1 part in about 5 million. Irrelevant for any human purpose. To reach the speeds where time dilation matters in a year-scale journey, we would need propulsion systems that don't exist. Antimatter drives, fusion ramjets, photon sails pushed by laser arrays the size of continents. All of these have been theorized. None of them have been built. None of them are close to being built. But the physics is patient. The physics doesn't have a deadline. It just sits there, correct, waiting. There are proposals for generation ships, spacecraft designed to carry humans across interstellar distances over multiple generations. Passengers would be born on the ship, live their lives on the ship, and die on the ship, with their descendants eventually arriving at the destination. But with time dilation operating at relativistic speeds, the generation ship concept gets complicated in ways that aren't always appreciated. If the ship travels fast enough to arrive within a few hundred years of Earth time, the crew on board might experience only a fraction of that. The society on the ship might be only a few generations deep. But Earth, at the other end, would have waited centuries. The civilization that sent the ship might look nothing like the civilization the crew left. Technologies would have changed enormously. Languages would have shifted. Political structures would be unrecognizable. The crew would arrive as living archives of a civilization that no longer exists in the same form. They'd carry the customs, language, memories, and cultural assumptions of a version of Earth that their destination Earth has long since moved past. And the people on Earth watching for the ship's arrival, they wouldn't be the same people who launched it. Not even their great-grandchildren would be. The launch and the arrival would be separated by such a span of time that the connection between them would be entirely historical. A record in an archive. A story told to children about the brave people who left. The crew wouldn't return to their world. They'd arrive at a successor to their world. Distant, related, recognizable in principle, alien in practice. This is the trap stated in its most human terms. Not a physical trap, not death, not injury, a temporal trap, a disconnection from the when you came from that no amount of courage or preparation can prevent. You chose to go far. The universe moved you forward instead. And forward, in time, is a one-way door. You've always known that. It turns out, the rate at which you pass through that door is negotiable. The direction is not. And here is the thing that the equations don't tell you, but that the numbers imply. Age is not just a number. It's a record. A record of every experience, every relationship, every loss and gain that accumulates in a human life. Time dilation doesn't just slow a clock. It slows all of that. It means the traveler accumulates fewer experiences, fewer sunrises, fewer conversations, fewer chances to change their mind, update their beliefs, or be surprised by something they didn't see coming. The traveler who returns after 3 ship years and 20 Earth years isn't younger in only the physical sense. They have 17 fewer years of experience than the people who stayed. 17 fewer years of watching what changes and what doesn't. 17 fewer years of the slow accumulation of context that shapes how you understand the world. The people who stayed are not just older. They're different. They know things the traveler doesn't. They've seen things the traveler missed. They've lost people the traveler was still expecting to see again. They've formed new attachments, new opinions, new habits. They've been shaped by years the traveler never experienced. The traveler stands at the arrival gate and the world looks familiar. But it's a world that has lived without them. And that's a kind of loneliness that has no word for it yet. A loneliness in time rather than in space. You're not far from the people you love. You're when from them. And when, unlike where, is a gap you cannot close by traveling. You can always travel back to a place. You cannot travel back to a time. This is why the title of tonight's video is not quite what it seems. The trap isn't the black hole. The trap isn't the singularity. The trap isn't even the end of a human life. The trap is simpler and more uncomfortable than any of those. The universe offers you speed. Real speed. The speed to cross vast distances in a human lifetime. The speed to go to places no human has ever been and come back having not aged much. That is genuinely on offer. The physics permits it. The option is real, in principle. But the price is not paid in energy alone. It's paid in time. Other people's time. Every hour you spend in motion near the speed of light, Earth runs ahead. People age. Events happen. Relationships end and begin and end again. History accumulates. And you don't accumulate it with them. You've been running a different clock. A slower clock. And when you step out of the ship, you find yourself in the future you chose without choosing it. You wanted to go far. You went forward instead. And going forward in time has always been, in every human story and every human instinct, a one-way door. You can move through time in only one direction. You always have. It just turns out the rate is negotiable. And that negotiation has a cost. The next time you use a navigation app, remember this. The satellite above you carries a clock that runs fast. Your phone corrects for it. And if it didn't, you'd be lost. The next time you fly across an ocean, know that the atomic clocks in the satellites guiding the plane lost time, while the ones that stayed on the ground did not. Not much. A few billionths of a second. But the effect is real. The equations work. The universe is doing exactly what Einstein said it would do. And what Einstein said it would do is this. Time is not yours alone. Time belongs to the geometry of the universe. It bends around mass. It stretches under motion. And the faster you move, the more it borrows from you. Not from your clock. From your life. The deeper you sit in a gravitational well, the slower your clock ticks relative to someone sitting in flatter spacetime. This has a consequence that most people don't pause on. It means that every massive object in the universe, every planet, every star, every black hole, has a different gravitational potential at different distances from it. And at each of those distances, time runs at a slightly different rate. The universe is not a single stage on which events happen at a uniform pace. It's more like an ocean floor of varying depth. Near the surface, in shallow water, things move quickly. Deep down, in the crushing pressure of the depths, things move slowly. The things, in this analogy, are clocks. Biological processes. The rate at which change happens. Near the surface of a neutron star, your biology would run at 70 to 80%, the pace it runs far away from any mass. Near the event horizon of a black hole, that rate would approach 0. And inside the event horizon, the concept of time as we know it breaks down entirely. Not because something mystical happens at the horizon, but because inside it, the geometry of space-time is so warped that the future, all futures, point toward the singularity. You can't move away from the singularity any more than you can move away from tomorrow. This is what physicists mean when they say the singularity is not a place. It's not at a position in space you can navigate around. It's at a moment in time that all interior trajectories are pointed toward. The singularity is an event you cannot avoid once you're inside the horizon. Because avoidance would require moving backward in time, and the universe doesn't offer that. Now consider what it means that all of this is happening everywhere, all the time, at scales too small to feel, but real enough to measure. At the National Institute of Standards and Technology, in Boulder, Colorado, physicists have built some of the most precise clocks ever made. The best of these optical clocks would neither gain nor lose 1 second in tens of billions of years. That's longer than the current age of the universe. With clocks this precise, you can measure gravitational time dilation over distances of centimeters. In 2010, researchers demonstrated this by comparing 2 aluminum-ion clocks at different heights. 1 foot of height difference, about 30 centimeters. The elevated clock ran faster, by a measurable amount. Not an enormous amount. Over a whole human lifetime, the difference would add up to roughly 90 billionths of a second. The clocks were precise enough to see the effect of 1 foot of altitude on the rate of time. 1 foot. This means that if you lie flat on the floor, the atoms in your head are genuinely, measurably aging faster than the atoms in your heels. Not by any amount you'll ever notice in a human lifetime. But the geometry of space-time doesn't care about whether you notice. It applies its rules at every scale, every mass, every altitude, every speed, every position in the universe, without exception, without negotiation, without any interest in whether the result is convenient for the observer. The question that often comes up at this point is, does this mean we could use time dilation deliberately? Could someone exploit these effects to achieve something useful? For gravitational time dilation, yes, in a narrow sense. If you were near a massive object and someone far away was experiencing time at a faster rate, you could use that difference. But the uses are limited. You can't travel back in time. You can only travel forward faster than you otherwise would, relative to objects in stronger gravity, or forward more slowly, relative to objects in weaker gravity. The direction doesn't change, only the rate. And the rate changes in ways that create problems as often as they create opportunities. For velocity-based dilation, again, the direction only goes one way. Travel fast, age slowly, arrive in the future. That's the offer. There's no corresponding offer to age quickly and arrive in the past. Physics is not symmetric about the direction of time in this sense. You can spend your future more slowly than the universe spends it. You cannot borrow from the past. The trap, the temporal exile, the one-way displacement is a feature of the physics, not a flaw. It's built into the geometry. It's what the equations predict. And no amount of cleverness, no matter how advanced the technology, will change it. Because you're not fighting an engineering limitation. You're fighting the structure of space-time itself. Something that gets lost in most discussions of time dilation is how it connects to the deepest questions about the nature of reality. Not philosophical questions, physical ones. What is the universe made of? What is time, really? Is time a dimension of the same kind as the three dimensions of space? Or is it fundamentally different? In Newtonian physics, time was a background, an absolute thing. A river that flowed at the same rate everywhere, carrying all of reality forward together. Events happened in time. The universe had an age, and that age was the same everywhere. Special relativity destroyed this picture. Time became a dimension, not an absolute background, a relative quantity. Something that different observers measure differently. Something that gets tangled up with space in the structure called spacetime. And general relativity deepened the picture further. Spacetime is not a rigid structure. It bends. It curves. It responds to the presence of mass and energy. It's not a fixed container that holds the universe. It's part of the universe. It participates in the physics. It has geometry that changes from place to place and moment to moment. And because time is part of space-time, time shares in all of this. Time is not a fixed river. It's more like a medium. A medium with its own geometry. A medium that responds to mass and motion. A medium that can be curved, stretched, compressed, and warped. And like any medium, it doesn't behave the same way in all environments. In the vacuum, far from any mass, at low velocity, it's relatively flat and regular. Near a massive body, it curves. Near a very massive body, it curves dramatically. And near an event horizon, it curves so extremely that the distinction between time and space breaks down in a way that changes what it means to move in any direction at all. This is not a flaw in our understanding. It's the structure of the universe we live in. A universe with this geometry, with these properties, that responds to mass and motion this way. We didn't choose this universe. We found ourselves in it. And what we've been doing for the last 100 years is reading the instructions it was kind enough to leave in the mathematics. One final thing worth sitting with. The universe is about 13.8 billion years old. In that time, it has produced an extraordinary range of environments. Some of them have been near supermassive black holes. Some have been in the deep voids between galaxy filaments. Some have been inside galaxy clusters, where the gravitational potential is deep. Some have been at the surfaces of stars. In each of these environments, time has run at a different rate. The universe's history has not unfolded at the same pace everywhere. Near the supermassive black holes that formed in the early universe and ate voraciously in the epochs astronomers call the quasar era, time ran slowly relative to the voids. In the voids, time ran fast. Over 13.8 billion years of cosmic history, these small differences have accumulated. A clock placed near a supermassive black hole at the beginning of the universe and left there would read a different age today than a clock placed in the void. How different depends on how close to the event horizon and for how long. But the principle is certain. The universe's age is not the same everywhere inside it. 13.8 billion years is the age in the reference frame of the cosmic microwave background, a kind of average or representative measure. But real clocks, placed in real environments throughout cosmic history, would disagree. This is not a paradox. It's not a contradiction. It's the geometry of the universe operating as designed. There is no single number that correctly describes the universe's age for all observers in all environments. There is only local time, only proper time, only the age of this place, in this reference frame, accounting for the mass that has been nearby and the velocities that have been experienced. The universe is not one clock. It's an uncountable number of clocks, all running at their own rates, none of them universal, all of them correct. And if you were to somehow travel between the most extreme environments, from the edge of a supermassive black hole to the deep void between clusters, you would find that the universe outside has aged enormously, while you experienced only moments. Or the reverse, if you stepped out of the void and into deep gravity. The universe offers no guarantee of consistency. It offers only the rules. And the rules say, mass curves time, velocity dilates time, and neither effect has a reversal. Move in, move fast, and you move forward. Always forward, into a future that has been running without you. There is something worth understanding about the history of how we came to know all of this. Because it didn't happen overnight, and it didn't happen in a vacuum. The physics of time dilation emerged from a long conversation between experiment and theory. A conversation that started with practical measurements and ended at the edge of what the human mind can comprehend. In the early 1800s, physicists were already wrestling with the speed of light. Ole Römer had made a rough measurement of it back in 1676 by watching the moons of Jupiter. He noticed that when Earth was moving away from Jupiter in its orbit, the timing of the moon's eclipses was slightly delayed compared to when Earth was moving toward Jupiter. He correctly interpreted this as evidence that light takes time to travel, that it has a finite speed. By the 1800s, measurements had improved dramatically. Jean-Bernard Léon Foucault measured the speed of light in the laboratory in 1850. Albert Michelson made increasingly precise measurements starting in 1878. By the time Einstein was born in 1879, the speed of light was known with considerable accuracy. and it was always the same, regardless of the direction of measurement, regardless of Earth's position in its orbit, regardless of how the experiment was designed. This bothered physicists enormously. Because in classical physics, in the physics of Newton and Maxwell, there should have been a medium through which light traveled. The way sound travels through air. The way ocean waves travel through water. Every wave they knew about needed a medium. So light needed one too. They called it the luminiferous ether, the light-carrying ether, a substance that filled all of space, absolutely at rest. The fixed background against which all motion was measured. The ether was supposed to explain why light traveled at a specific speed. It was the medium that set the speed, just as the density and elasticity of air set the speed of sound. The problem was that if the ether was real and absolutely at rest, then Earth's motion through it should be detectable. If you're moving through a medium, waves moving with your motion appear slower to you, and waves moving against your motion appear faster. So the speed of light should vary depending on the direction you measured it. It didn't. The Michelson-Morley experiment in 1887 was the definitive test. Michelson built an interferometer so sensitive it could detect a change in the speed of light of 1 part in 100 million. He split a beam of light into 2 perpendicular beams, sent them out and back along different axes, and looked for interference patterns that would reveal a difference in the time it took each beam to return. If the ether existed and Earth was moving through it, the 2 beams should return at slightly different times, creating a detectable interference pattern. No pattern appeared. The 2 beams returned at exactly the same time, every direction of measurement, every time of year as Earth moved around the sun. No difference. Ever. The ether didn't exist. And if the ether didn't exist, if there was no fixed medium, no absolute rest, no privileged reference frame, then physics had a problem. Maxwell's equations predicted a specific speed for light. But which reference frame was that speed measured in? If there was no special frame, then the speed had to be the same in all frames. But that contradicted everything else in classical mechanics. That's the wall that Einstein walked up to in 1905. And instead of trying to patch the wall, he walked through it. He said, "Fine. The speed of light is the same in all frames. Let's follow that to its logical conclusion." And what followed was special relativity and time dilation and everything we've been talking about tonight. It's worth pausing on what Einstein actually did in 1905, because it's easy, looking back, to see it as inevitable. Of course, he was right. Of course, the physics worked out. But at the time, accepting Einstein's postulates required a profound act of intellectual courage, because the consequences were absurd. Time runs differently for different observers. Moving objects are shorter in the direction of motion. 2 events that are simultaneous for one observer are not simultaneous for another. These weren't just unfamiliar ideas. They contradicted every intuition built into the human brain by millions of years of evolution, in a world where speeds are always tiny fractions of light speed. Our brains are not built to experience relativistic effects. We evolved to catch prey, avoid predators, build shelters, plant crops. None of those activities require understanding what happens when clocks move at 90% of the speed of light. The physics of everyday life is Newtonian. It's the physics of objects that move slowly, of forces that are proportional to mass times acceleration, of time that ticks uniformly. And Newtonian physics was enormously successful. It predicted the motion of planets with stunning accuracy. It explained the behavior of gases and fluids and solids. It undergirded the entire Industrial Revolution. It was, and remains, an extraordinarily powerful description of reality at human scales. The problem was only at the edges, at speeds approaching light, at gravitational fields of extreme strength, at distances and times of cosmic scale. That's where Newtonian physics failed. And Einstein's genius was recognizing that the failures at the edges weren't anomalies to be patched. They were clues. Clues that pointed toward a deeper, stranger, more complete picture of reality. A picture in which time is not fixed. In which space and time are two aspects of a single four-dimensional fabric. In which mass curves that fabric. In which the speed of light is the fundamental constant that ties it all together. The picture we now call the theory of relativity, confirmed by every experiment ever designed to test it, confirmed by the operation of GPS satellites, confirmed by the detection of gravitational waves by LIGO in 2015, confirmed by the imaging of black hole event horizons by the Event Horizon Telescope, confirmed by the precise measurement of the Muon anomalous magnetic moment, confirmed by hundreds of experiments over 120 years. The picture is correct. We know it's correct. And the time dilation it predicts is not an artifact of the mathematics. It's a real, measurable, physically experienced fact about the universe we live in. There's a consequence of all this that most people never arrive at. It has to do with what we mean by the age of the universe. We say the universe is 13.8 billion years old. That number comes from measuring the expansion rate of the universe, working backward to the Big Bang, and calculating how long ago that was. But age is a measure of proper time, of experienced time, of the time measured by a clock at a specific location, following a specific path through spacetime. And different locations in the universe have experienced different amounts of proper time since the Big Bang. A hypothetical clock placed near the event horizon of a large black hole at the beginning of the universe and left there, continuously subject to severe gravitational time dilation, would read a smaller number today than 13.8 billion years. Because time near that event horizon has been running slowly, relative to the average. A hypothetical clock placed in the deep void between galaxy filaments, far from any significant mass, would read a number close to 13.8 billion years. Because that clock has been running close to the cosmic average rate. These aren't theoretical abstractions. They're physical predictions of the same equations that explain GPS satellites and muon survival rates. The 13.8 billion year age of the universe is a statement about time experienced in a specific reference frame, roughly the reference frame of the cosmic microwave background, the afterglow of the Big Bang. It's a useful and meaningful number. But it's not the age of the universe as experienced by every part of the universe. Different parts have experienced different amounts of time. The universe is not uniformly old. It is old in different amounts, in different places, according to the mass distributions and velocities that have prevailed in each location over cosmic history. That's a strange thought to sit with. The universe is not a single entity that has existed for a fixed duration. It's a collection of local environments, each with its own time, each running at its own rate, each accumulating its own age at a pace determined by local physics. The universe is simultaneously 13.8 billion years old, and less than that in some places, and perhaps slightly more than that in others. Not because the clocks are wrong, because the clocks are right, and the universe is genuinely this way. One more thing about black holes. We talked about what happens when you fall in. We talked about what happens when you orbit nearby. But there's a third scenario that doesn't get discussed as often. What happens when a black hole approaches you? Or more precisely, what happens when the gravitational influence of a black hole reaches your location as the black hole moves through space? Black holes aren't stationary. They orbit in galaxies. They merge with other black holes. They pass through regions of space that contain stars and gas and potentially civilizations. The gravitational time dilation that a black hole creates extends far beyond its event horizon. It weakens with distance. More precisely, it falls off in a way that depends on the mass of the black hole and your distance from it, but it doesn't drop to zero. Far from a black hole, the effect is tiny. But for a sufficiently massive black hole, passing sufficiently close, the gravitational influence would create a detectable time dilation, even at large distances. Detectable by a precision clock. Perhaps detectable by sensitive instruments. Perhaps, in principle, detectable by biological systems sensitive enough to notice subtle changes in the rate of physical processes. We have no evidence that any black hole will come close enough to Earth for this to matter in any practical sense. Our galaxy's supermassive black hole Sagittarius A is about 26,000 light-years away. Its influence on time at Earth's distance is negligible. The nearest stellar mass black holes are at least several thousand light-years away, also negligible. But the principle is there. The universe contains moving concentrations of mass that create local regions of differently running time. Those regions are real. They're happening right now. And any object that passes through them enters a slightly different temporal environment for the duration of its passage. The universe is full of these variations. Most of them too small to matter for anything we can currently measure. But the variations are real, and in extreme cases, they become not just measurable, but transformative. The same physics that creates a 38 microsecond correction in a GPS satellite creates the billion-year time divergence near the event horizon of a supermassive black hole. It's the same physics, the same equations, the same geometry, just different numbers plugged in. And the numbers the universe can plug in are much larger than the numbers we encounter in daily life. Much, much larger, with consequences that scale accordingly. Something that Einstein himself grappled with is the question of whether time dilation implies that the past and the future exist in some real sense. Not as memories or anticipations, as physical realities. In special relativity, the question of whether two distant events are simultaneous depends on your reference frame. Events that are simultaneous for you are in different nows for an observer moving differently. An observer moving toward a distant galaxy might say that what's happening right now on a planet in that galaxy is something that, from your perspective, hasn't happened yet. For them, it's now. For you, it's the future. This suggests that the future, in some sense, is already there, already laid out in space-time, already existing, just not yet reached by your now. This is the block universe interpretation of special relativity. The idea that spacetime is a four-dimensional block, a static structure, in which all events, past, present, and future, exist simultaneously as features of the geometry. What we experience as time passing is not time passing in any absolute sense. It's our consciousness moving through the block, reading one slice of space-time after another. The block doesn't change. We move through it. This interpretation is philosophically uncomfortable for many people. If the future already exists, what does it mean to make a choice? What does it mean to act? What does it mean to be responsible for anything? These questions don't have easy answers. They sit at the boundary between physics and philosophy, and honest physicists acknowledge that. The mathematics of special relativity is clear. The physical interpretation is contested. The block universe is one consistent interpretation. There are others. And the mathematics doesn't, on its own, tell us which interpretation is correct. It tells us what will happen. It doesn't tell us what time is. That remains genuinely open. One of the deepest open questions in physics, which is, in its own way, one of the most astonishing things about where we are. 120 years after Einstein, after a century of experimental confirmation, after GPS and atomic clocks and gravitational wave detectors and event horizon telescopes, we still don't fully know what time is. We know how it behaves. We know what it does. We know how to predict, with extraordinary precision, what it will do under any conditions we've been able to test. But the question of what it is, what kind of thing it is, remains genuinely, honestly, humbly open. And there's something right about that. Something that feels like the universe maintaining a little mystery, giving us enough to work with, enough to navigate by, enough to build civilization on, but keeping its deepest nature to itself, for now. There is one more effect that deserves careful attention before we close. Something that ties the velocity effects and the gravitational effects together in a way that reveals how unified the physics really is. It's called gravitational redshift, and it's both a confirmation of general relativity and a direct consequence of gravitational time dilation. When light is emitted from deep inside a gravitational field and travels outward to a region of weaker gravity, something happens to it. Its frequency decreases. Its wavelength increases. It shifts toward the red end of the spectrum. This is gravitational redshift. And it happens for a reason that is directly connected to everything we've been discussing. Think of it this way. An atom emitting light at the bottom of a gravitational well is like a clock ticking at the bottom of the well. It emits a certain number of wave crests per second of its own local time. But its local time is running slowly compared to the time at the top of the well. So when you count those wave crests at the top of the well, using the faster running clocks at the top, you count fewer crests per second. The frequency is lower. The light has been redshifted, not because the photons lost energy in some mechanical way during flight, but because the rate at which they were emitted, measured in units of the emitter's local time, translates into a lower rate when measured in units of the receiver's local time. Time dilation is the cause. Redshift is the observable consequence. This effect was confirmed by Pound and Rebka in their 1959 Harvard experiment, and it's been confirmed many times since. The light from the surface of the sun is measurably redshifted compared to the same spectral lines produced in a laboratory on Earth. By a small amount, the Sun's gravity is relatively mild. But, measurably, the light from white dwarf stars is redshifted by more. White dwarfs are much denser than the Sun, with stronger surface gravity. The light from neutron stars is redshifted dramatically. Their surface gravity is hundreds of billions of times stronger than Earth's. And as you approach the event horizon of a black hole, the redshift of light emitted from near the horizon grows without bound. Photons, trying to escape from just outside the event horizon, are so redshifted that they arrive at distant detectors with almost no energy at all. From infinitely close to the event horizon, the redshift would be infinite. The photon would arrive with zero energy. It wouldn't arrive at all. This is why black holes are black. Not just because objects falling in can't escape, but because even light emitted from just outside the event horizon is so severely redshifted that it's effectively invisible. It's worth letting that sit for a moment. A light source sitting just outside a black hole's event horizon is emitting photons. Real photons carrying real energy. But by the time they climb out of the gravity well to a distant observer, they've lost so much energy to the redshift that they carry almost nothing. They've spent everything they had just escaping. Gravitational redshift is time dilation expressed in the language of light. And it tells us something profound. The universe, in the regions near black holes, is communicating with us only in whispers. Whispers stretched so red, they're barely audible. The full story of what's happening near a black hole's event horizon is inaccessible to us. Not because we lack the instruments, but because the physics prevents the signal from reaching us with its full content intact. The information is redshifted away, which is itself a kind of trap. A trap for knowledge. A wall built not of matter, but of geometry. There's an interesting parallel between gravitational redshift and the Doppler effect that most people have experienced without thinking much about it. The Doppler effect is the change in the frequency of a wave when the source or observer is moving. You've experienced it every time an ambulance passes. The pitch of the siren is higher when the ambulance is moving toward you, lower when it's moving away. The sound waves are compressed in front of the moving ambulance, raising their frequency, stretched out behind it, lowering their frequency. Light obeys a relativistic version of the same principle. When a galaxy is moving away from us, its light is redshifted. When it's moving toward us, its light is blue-shifted. The redshift of distant galaxies is how we know the universe is expanding. Edwin Hubble measured the recession of galaxies in 1929, finding that almost all galaxies are moving away from us, and the farther away they are, the faster they're receding. This was the first observational evidence for the Big Bang. But what Hubble measured was velocity-based redshift, the Doppler effect. Gravitational redshift is different. It's caused not by motion, but by gravity, by the curvature of spacetime, by the fact that time runs at different rates, at different depths in a gravitational well. In practice, astronomers have to account for both effects when analyzing spectra from distant objects. Galaxies near massive galaxy clusters can show a combination of gravitational redshift from the cluster's gravitational potential and velocity redshift from their orbital motion within the cluster. Disentangling these requires careful modeling. But both effects are real. Both are measured routinely. Both confirm the physics. And both trace back to the same underlying picture. Time is not uniform. Space is not flat. The universe has a geometry that affects both the paths of objects and the rates at which events unfold. And that geometry is governed by the distribution of mass and energy in the universe, which changes over time, as stars form and burn out, as galaxies merge, as black holes grow. As the universe expands and the average density of matter decreases, the geometry of space-time is not fixed, it evolves. And as it evolves, the rates at which time runs in different locations evolve with it. The universe, in its early, dense phase, had a very different gravitational geometry than the universe today. And the universe, billions of years from now, will have a different geometry still. Time itself will have a different character. Not in a mystical sense. In a precisely quantifiable, experimentally confirming, mathematically tractable sense. The universe's relationship with time is not simple. It was never simple. We just lived in a corner of it where the complications were too small to notice. Until we looked closely enough. Understanding time dilation at a deep level requires accepting something that cuts against some very strong intuitions. We tend to think of our experience as the standard, as the reference point, as the thing that other experiences should be measured against. You experience time passing at a certain rate, 1 second per second. And you naturally assume that's the rate at which time passes for everyone. But it's not. It's the rate at which time passes for you, in your particular location, at your particular speed, in your particular gravitational environment. Every observer in the universe has a rate at which time passes for them. And all of those rates are equally valid, equally real, equally correct descriptions of their local experience. None of them is the standard. None of them is the right rate. They're all right, for their respective reference frames. This is not relativism in the philosophical sense. It's not saying that all perspectives are equally accurate descriptions of objective reality. The objective reality is space-time, the four-dimensional fabric. And that fabric has a definite structure, a definite geometry, a definite set of relationships between events. But the rate at which time flows through that structure is not fixed. It varies. And every observer's experience of that varying rate is a valid, accurate, real experience of the universe they inhabit. This is what Einstein meant by relativity. Not that everything is relative in the sense that nothing is objective, but that measurements of time and distance are relative to the observer, while the geometry of space-time itself is objective, is the same for everyone, is a real structure with real properties, just not the simple, fixed, Newtonian structure we assumed. It's curved. It's dynamic. It responds to mass and energy. And it treats time as a participant, not a background. The practical implications of all this for any future civilization that ventures beyond the immediate solar neighborhood are immense. Not just in the ways we've discussed the temporal exile, the displacement from the when of origin, but in the engineering, in the communication, in the social structure of any community that lives at different points along a gradient of gravitational time dilation or at relativistic speeds relative to each other. If two spacecraft are traveling at different fractions of light speed, they age at different rates. If they communicate, they have to account for the rate at which time is running differently for each crew. Not just the signal delay from the distance between them, but the actual difference in the rate of their clocks. If a colony is established in orbit around a massive body a neutron star, a white dwarf, anything significantly more massive than the planets we live near, the colonists will age more slowly than people on Earth. Over centuries, the age gap accumulates. A child born on Earth and a child born in that colony on the same day, by the calendar of someone watching both from far away, will be different biological ages if they meet 100 years later. The colony child will be younger, not slightly younger, measurably, biologically younger. And if the difference in gravitational environment is large enough, if the colony is sufficiently deep in a gravitational well, the gap could be years or decades. Over the lifetimes of multiple generations, the accumulated difference becomes a genuine cultural and biological divergence. The people in the gravitational well age more slowly. They have more time, in some sense. They have fewer years of experience for each calendar year that passes outside. They are perpetually the younger civilization, relative to the one in weaker gravity. These are not hypothetical concerns for some far future. They are the natural consequences of the physics we already understand, applied to scenarios that are simply further along the technological and civilizational development curve than where we currently are. The physics is already written. The consequences are already known. Anyone who builds civilizations at different gravitational potentials will have to grapple with them. As surely as GPS engineers had to grapple with 38 microseconds per day, and beneath all of it, underneath the GPS corrections and the muon detectors and the black hole orbits and the interstellar mission plans, there is a fact so simple it almost doesn't feel like a fact. It feels like a discovery. Time is yours, but only in the sense that it's the time you experience. The time that passes in your reference frame, the time that your biology tracks, the time that your memories are made of. In that sense, time is deeply personal. It belongs to you in the way your heartbeat belongs to you. But it doesn't belong to you in the sense of being universal. In the sense of being the time. There is no the time. There is only your time. My time. The time experienced by a muon in a cosmic ray shower. The time experienced by a GPS satellite in orbit. The time experienced by a hypothetical astronaut orbiting a spinning black hole 3 light-years from Earth. Each of these times is real. Each of them is valid. None of them is the standard. And when you move through the universe fast enough, or fall deep enough into a gravitational well, your time begins to diverge from everyone else's. Not in a way you can feel. Not in a way that announces itself. Just quietly, steadily, invisibly. The clocks pulling apart. The ages diverging. The shared when dissolving into individual whens. Until, at the extreme, you look up from the ship or the orbit and find that the universe you came from is gone, not destroyed, not lost, just past, moved forward without you, into a future you couldn't have predicted and can't return from. That is what time dilation is, in the end. Not a curiosity, not a technicality, not an effect relevant only to particle physicists and GPS engineers. It is the universe telling you that time is not the shared ground you thought it was, that the floor beneath you has always been moving, at rates you couldn't feel, measured in nanoseconds, in microseconds, in milliseconds, building, over time, over distance, over extremes of mass and velocity, into something you could never come back from. The universe has been saying this since Einstein wrote it down. We're still learning to hear it. There's something worth saying about the experimental tradition that produced all of this knowledge. Because it didn't come easily. It came from generations of physicists who were willing to do something difficult, to follow the mathematics wherever it led, even when it led somewhere that contradicted every intuition they had. The Michelson-Morley experiment failed to find the ether. Lorentz and Fitzgerald responded by proposing that objects physically contract in the direction of their motion through the ether, that the contraction was just enough to explain the null result. It was a patch, an ad hoc fix to save the ether theory. Einstein's response was different. He said, maybe there is no ether. Maybe we don't need it. Maybe the null result isn't something to be explained away. Maybe it's telling us something fundamental about the universe. And he followed that thought all the way to its conclusion. The speed of light is constant for all observers. No ether required. No preferred frame required. Just the constant. And then he did the mathematics. And the mathematics said, time dilates. Space contracts. Simultaneity is relative. And energy equals mass times the speed of light squared. The last one, by the way, is a consequence of the same postulates. E equals mc squared is not a separate discovery. It's the same relativity applied to the relationship between mass and energy. Mass and energy are the same thing, seen from different perspectives. A fact so strange that even Einstein initially wasn't sure how to interpret it physically. But the mathematics was clear. And the mathematics has always been right. Every time, without exception. In every experiment ever designed to test it. Let's talk about what happens to light itself near a black hole. Because light is not immune to gravity. One of the first confirmations of general relativity came from exactly this. In 1919, just 4 years after Einstein published General Relativity, a British expedition, led by Arthur Eddington, observed a solar eclipse. During the eclipse, with the sun's disk obscured, it was possible to observe stars near the sun's edge. Stars that would normally be hidden in the sun's glare. Einstein had predicted that the sun's gravity would bend the path of light from those stars. That starlight passing close to the sun would curve slightly, making the stars appear to be in slightly different positions than expected. The amount of bending he predicted was about 1.75 arcseconds. A tiny angle, but measurable. Eddington's team measured it. The stars were displaced by almost exactly the predicted amount. Light bends around mass. Gravity doesn't just affect objects with rest mass. It affects everything that travels through spacetime, including light, including the photons that carry information, and including time itself, which is woven into spacetime alongside space. Near a black hole, the bending of light becomes extreme. At the photon sphere, a radius about 1.5 times the Schwarzschild radius, around a non-rotating black hole light, can orbit the black hole. Photons can travel in circles. They can orbit the singularity endlessly, going nowhere except around and around. If you were standing just outside the photon sphere and looked tangentially, you would see the back of your own head. Light from you would curve around the black hole and come back. It's not a mirror, it's a gravitational lens. And beyond the photon sphere, toward the event horizon, the curvature becomes more severe still. Any photon that crosses the event horizon from outside is captured. It cannot escape. It will spiral inward to the singularity. And any signal emitted from inside will also spiral inward. Nothing that crosses that boundary comes back out. Not light. Not time. Not information. The event horizon is, in the most literal physical sense, a one-way door. And on the other side of that door, time runs differently. Not just slowly. Differently in kind. In a way that makes the concept of later point only toward the singularity. In a way that makes escape not just difficult, but geometrically impossible. This is what Karl Schwarzschild's solution described a century ago in a trench on the Eastern Front, and it's what we've been observing ever since. In the orbits of stars around Sagittarius A, at the center of our galaxy. In the gravitational waves from merging black holes detected by LIGO. In the image of M87's event horizon captured in 2019. The universe has confirmed the physics at every turn. And the physics says this: time is real. Time is physical. Time bends and stretches and slows, and, at the event horizon of a black hole, reaches a point where the concept itself requires careful re-examination. That's not a failure of the theory. It's the theory working exactly as designed, pointing us towards something we don't yet fully understand, inviting us to go deeper. There's one final idea worth landing on, something that puts all the rest in context. The universe is under no obligation to be navigable by human intuition. It was not built for us. It existed for roughly 9 billion years before our sun ignited, for another several 100 million years before Earth formed, for billions of years after that, before anything resembling human life appeared. The laws of physics were not written to be convenient for minds that evolved to track prey on an African savanna. They were not adjusted to make sense at human speeds, human scales, and human lifetimes. They're just the laws, applicable everywhere, at all speeds, at all scales, at all gravitational potentials. And what those laws say is this: time is not a fixed constant that flows uniformly through all of space for all observers. It never was. We simply spent most of our history moving too slowly and living too close to each other and sitting in too similar a gravitational environment to notice the difference. The difference was always there, measured in nanoseconds, in attoseconds, in fractions too small for any instrument we had for most of human history to detect. But it was there, in the light from stars, in the orbits of planets, in the behavior of every atom in the universe. The truth was written into the fabric of reality from the first moments of the Big Bang. We just needed the mathematics and the instruments and the willingness to follow the logic wherever it led, to read it. Einstein read it in 1905. Pound and Rebka measured it in a Harvard building in 1959. Hafele and Keating confirmed it on commercial flights in 1971. GPS engineers built it into satellites starting in the 1970s. And every experiment since has confirmed what the mathematics said. The universe bends time around mass, under motion, without asking permission, without offering exceptions, without caring whether the outcome is convenient for the beings who figured it out. It just does it, continuously, everywhere, at every scale, From the attosecond difference between your feet and your head to the billion-year difference between a clock near a black hole and a clock in the deep void. Same physics, different numbers. And if you ever find yourself in a situation where the numbers are large, where the mass nearby is enormous, or the speed is significant, or both, the physics will apply to you exactly the way it applies to everything else. You will age more slowly. The universe will age more quickly around you. The gap will open, and it will not close. That's what time dilation is. That's what Einstein found. That's what the muons confirm, and the GPS satellites confirm, and the supernovae confirm, and the gravitational wave detectors confirm. The universe has been telling us this for 120 years. We've been listening. The next time you use a navigation app, remember this. The satellite above you carries a clock that runs fast. Your phone corrects for it. And if it didn't, you'd be lost. The next time you fly across an ocean, know that the atomic clocks in the satellites guiding the plane lost time, while the ones that stayed on the ground did not. Not much. A few billionths of a second. But the effect is real. The equations work. The universe is doing exactly what Einstein said it would do. And what Einstein said it would do is this. Time is not yours alone. Time belongs to the geometry of the universe. It bends around mass. It stretches under motion. And the faster you move, the more it borrows from you. Not from your clock, from your life. Look up tonight at any bright star you can see. The light arriving at your eye left that star years ago, centuries ago. Some of it thousands of years ago. The star you're looking at is not the star as it is. It's the star as it was. You're looking into the past. The universe doesn't show you the present. It shows you a record of what was. And somewhere out there, around one of those stars, there might one day be a human being looking back toward our sun, looking at light that left Earth while we were alive, seeing us not as we are, as we were, frozen in light, permanent, which is its own kind of trap and its own kind of beauty. If you've made it this far, consider liking this video or subscribing to the channel. It's the best way to stay connected as we keep going deeper. Good night.